Alrighty, so a little bit of molecular orbital theory. So the main idea behind molecular orbital theory is that atoms want to go from a higher energy to a lower energy by combining together to make molecules. So when we have atomic hydrogen, where it just has a proton and an electron, they're flying around, they're going to want to get together to become H2. So how does this happen? As these two atoms are getting closer together, their electron clouds around each other are being attracted by the other's nucleus. So this nucleus is attracting this electron cloud, while this nucleus is attracting this electron cloud. This comes from our Coulombic force, where the force between these is relative to the charges and the distance. So as these get closer and closer together, this force is going to start growing as this distance gets smaller. So as these get closer and closer together, there's going to be a point where there is a super high chance for electrons to be found between the two nuclei, because the nuclei are attracted to the electron, but they're also repelling each other because they're both the same charge. This is where we get our idea of bonding. And so this is where our molecular orbital diagram comes in, is we have a 1s orbital, we have our s orbital for our hydrogen here, our atomic hydrogen, and we have our other atomic hydrogen, and as they get closer and closer together, they're going to start lowering in energy until they make our single bond. We're going to take one electron from here, bring it down here, the other electron from here, bring it down here. And so this is what explains our actual molecule of H2. Instead of just thinking of it as these two atomic orbitals, now we're thinking of it as one thing, with these two electrons having the same chance of being found together here, and there's a high chance in the middle. They could be anywhere inside these orbitals, but there's a high chance that they're going to be between the nuclei. Okay, but what does this mean? What does our anti-bonding mean? So anti-bonding is where one of our phases, so you can think of our orbitals as having sort of a plus side and a minus side. It comes from the idea that these are wave functions, that they can be either on the plus part of the wave or the minus part of the wave as they oscillate up and down. So for this one, if we're anti-bonding, it means that one of our wave functions is now changed to the other sign. So if we're bonding, we have positive and positive, or negative and negative. It's the same thing. It both makes this bonding sigma bond. If we have two separate ones, if we're like subtracting this and this and this and this, it'll make it where we have one of our wave functions become negative. And when this happens, this is where we get anti-bonding from. So the exact same amount of electron chance we have here in the middle will have the exact same amount of electron no chance here in the middle. Because as the great scientist Paula Abdul so aptly put it, opposites attract. So these things are going to be attracting here. Whereas when these two things change, this is going to be the electron density over here, and then our other electron density is going to be over here, exposing these two nuclei to each other. So this thing's positively charged, this thing's positively charged, and when we have two positively charged things exposed to each other, they're not going to want to be there anymore. So they're going to split apart. So this is where we get the idea for helium. Helium doesn't want to bond, and we can explain that using molecular orbital theory. So for helium, it'll have two 1s electrons for each of its atomic orbitals. And so when we combine them together, we'll fill up two of our molecular orbitals here, two into this sigma molecular orbital. But we'll have to keep up with the same amount of electrons we have on either side. So we've got two here, we're going to have 4 total here in the middle. And since we have one atomic orbital here and one atomic orbital here, 2 atomic orbitals total, we're going to have 2 molecular orbitals total. And so our 2 electrons go into here, our other 2 electrons go into our antibonding. If we have electrons in our antibonding molecular orbital, it scoops out the electron density here between our 2 nuclei, and it makes it where they will not bond. So this is where we get our whole rationale on why noble gases won't bond with each other, why they're monatomic instead of diatomic like our H2 here. So all this to say, we can use this with organic chemistry using p orbitals instead of our s orbitals. So for our p orbitals, they can be in phase like this. They can have plus plus and minus minus interaction, and this gives us a pi bond. Or they can have a pi anti-bonding interaction where we have plus and plus and minus and minus. The plus and minus are going to go together, and the plus and minus here are going to go together. So this makes it where we have destructive interference, or where our anti-bonding molecular orbital is going to be filled. And that makes it where our bonding starts breaking down. So how does this fit into aromaticity? So we go to our simplest aromatic compound, ethene. Remember, the qualifications for aromaticity are that it has to be planar, it has to be sp2 hybridized, and it has to be in the Huckel rules, which we'll get to in a second. But our ethene fulfills all those, and so lower in energy than our normal p orbitals, our pi bonding is going to take the 2 pi electrons down here. So the main idea behind aromaticity using molecular orbitals is that we want everything to be in the lowest energy it can, as far down as it can go, and we don't want any of our molecular orbitals to be partially filled or not filled. So in this case, ethene works because our lowest molecular orbital is filled, and we're lower in energy, and it fulfills all the other qualifications for aromaticity. We go to benzene, which is the most common example of being aromatic. And since we have 6 p orbitals in our working together to make our pi ring, we have 6 molecular orbitals. And as we can see here, all of our low energy molecular orbitals are completely filled. And since it follows all the other rules of aromaticity, this comes out to show us that benzene is in fact aromatic. Versus, say, something we have like this diene here, where only a few of our low energy molecular orbitals are filled, or they're partially filled. This means that this is not aromatic. So this is where we get our 4n+2 rule. If we can plug in a number here, and it comes out to be the number of electrons that we have in our molecule that we're looking at, then that means that we have an aromatic compound. So if we look at our ethene, if we did 0 as our n, so 4 times 0, 0 plus 2, that makes it where we have 2 pi electrons. That means that we are good, we are aromatic. For benzene, we can check it too. If we do 1 as our n, 4 times 1 plus 2 gives us 6. We have 6 pi electrons here, or p orbs, or p orbitals. Then we are good. If we have, is there any way we can get 4? No, there's not, because this plus 2 always screws it up. So this n has to be a whole number, and we can get, we can find out if this is aromatic. So this is the key. This is the thing that Dr. Ray is looking for, if you know this 4n+2 rule. Because if you can use this 4n+2 rule, you don't have to worry about any of this. So this is just so that you understand where the 4n+2 rule comes from. Okay, if I rushed through any of that or none of it made sense, let me know. I'll see you guys later.